Hi everyone, welcome to lesson 13.4. This is our last lesson that we're going to cover in chapter 13, and it's going to discuss a measure of curvature, a way of describing how sharp the curves are on a curve that's either in the plane or in space. And then we'll talk about the use of a vector called the normal vector to a curve. We're used to tangent vectors, but we want to describe a normal vector. So you can relate that back to the normal vector to a plane. And it might help you to understand that a little bit. Since we're not going further in chapter 13, I'll just remind you of something I mentioned in the last video. When we talk about a Frenet frame, we'll be talking about the vector t, the tangent, unit tangent vector. We'll be talking about n, the unit normal vector, and then the third vector we're not covering is in later material in chapter 13. So that particular aerospace application, we're going to miss out that last vector to create that three space that we could orient any way we want. And I really encourage you to watch the movie Hidden Figures if you haven't seen it already and look for the mention of that. It's closer to the end of the movie. Okay, so we're going to work in 2 dimensions for a while. This works the exact same way in 3 dimensions as it does in 2, again, with the concept of expanding from 2 to 3 dimensions, as we've seen multiple times in this course. It's just a matter of including the vectors in the z direction, including an axis in the z direction according to the right-hand rule of thumb, and works the exact same as it does in 2 dimensions. So we're just going to work in 2 dimensions for a while, and I'll let you explore the 3 dimensions on your own at the end to control the length of this video. So here we go. We've got the first image in our chapter is a familiar one, just tangent vectors drawn along a curve, except in this class we've added the focus on paying attention to the direction that a particle would move along the curve, so moving in the direction of increasing arc length. You can always see the little arrow down here. And then just a reminder that t is 1 unit long. It is called the unit tangent vector, and we learned about it in a previous section. But we're going to explore that a little bit more here as it relates to a measure of how curvy something is called curvature. And so as you move along this curve, the unit tangent vector changes directions. It's always 1 unit long, but it changes directions. And the rate at which it changes directions is going to give us an idea of how curvy the line is. So our unit tangent vector t is the rate of change of our position vector r as it relates to movement along the arc length ds. So dr ds. Okay, and we call that curvature. And so we've got the Greek letter kappa. It's a lowercase k sound, or k and c sound. There's no c in the Greek alphabet, so all of the k sounds in Greek are represented with a c. Excuse me, with a k for kappa that you see. I'm trying to think. You don't really see the capital kappa in math class. You might see it in science, but the lowercase kappa is what we're using here. And you can see that if we take the magnitude of t with respect to s, or the change in t with respect to s, we get a scalar quantity that tells us curvature. Okay, so we're going to need to change this. I like the way they describe this over here, but we're going to need to change it because curvature, we don't often work in terms of arc length, okay? So understand that curvature is a scalar number, not a vector. When it's close to 0, we've got fewer sharp turns on our curve, so it turns more slowly at a given point. So a smooth, wide open curve, a higher value of curvature means that t turns very sharply and maybe makes the curve look more jagged. All right, and so we're going to convert our formula for kappa with respect to arc length into a formula with respect to t, since that is WRT, remember, means with respect to the change in t, because that's much more useful. We're usually given position vectors r of t, so we're very rarely given position vectors r of s, and this won't be the last time we deal with this concept, but here we go. We're going to put in this neat little trick that you can see that the magnitude of dt ds is the same as the magnitude of this expression. Technically, if we canceled out the dt's, they would be identical. Okay, so we're just applying the chain rule here, kind of expanding this out so that we can rearrange and manipulate some things here. So if we pull out the scalar quantities here, we get 1 over the magnitude of ds dt. Pull it out, since these aren't vectors, then they don't have to stay in the magnitude bars up here for the whole expression. But we know the change in position s with respect to the change in time is velocity, and we need the magnitude, and that is a vector. And then we still have the multiplier dt dt. So make sure you distinguish between capital T here and lowercase t here. So here is our formula for curvature with respect to the change in time, or t, or whatever t stands for. All right, so that's our official formula here. Just remember that t is always the unit vector in the direction of the velocity, okay? So we're going to apply this idea to an actual curve. So here we go. Here we find the curvature of a circle. So we're going to begin with our parameterization of a circle of radius a. So the a is the multiplier in front of the trig function. And so you can always pick out the radius of a circular curve that's been parameterized as a vector valued function here. So see, it reminds you, circle of radius a. Okay, so in order to find the curvature, we're going to need dt dt, we're going to need v. All right, so those are important things to find. So I'm just going to start off with finding t, okay? And t is the vector divided by the velocity vector divided by its own length. So we need to find v of t, and that's just the first derivative. So we're going to have derivative of a cosine t is negative a sine t, and that's the I component. And then the derivative of a sine t is going to be a cosine t, and that's the j component. If this were in space, there would be a k term. Okay. Well, the magnitude of this vector is going to be the square root of a squared sine squared of t plus a squared cosine squared of t. All right, and we're going to simplify this. And I'm only going to do this once because this process pops up several times in the sample questions in this section. But I'm going to factor off a squared, and it leaves sine squared of t plus cosine squared of t behind. And we know this is 1, so the square root of a squared would simply be the absolute value of a. And since a is a radius, we already know it's positive. It's just going to be a. Okay, so we're going to take our velocity vector, divide the a's out, and we're going to end up with negative sine t I plus cosine t j. All right, so there is our t vector, and now we need to install it into this formula for curvature. Let me do that in a different color. So kappa, or curvature, equals 1 over the length of v, which we determined to be a, times dt dt. So we have to take the derivative here with respect to t. So the derivative of negative sine t is negative cosine t. And we're doing magnitude, that's right. Almost forgot. We're doing the magnitude of dt dt. So let me focus on dt dt down here. So we'll get the derivative first, and then we'll take its magnitude, okay? So the derivative of this vector is going to be negative cosine t I. And then, not plus. We're going to do, back up. We're going to do derivative of cosine t, which is going to be minus sine t j. Okay, just checking my notes, make sure I'm doing this well. So we got minus minus. Alrighty, and then we're going to take the magnitude of this, which would be the square root of cosine squared plus sine squared, which is the square root of 1, or just 1. So the curvature here is 1 over a times the magnitude of dt which is 1, which is just 1 over a, 1 over the radius. is the curvature of a circle. So here's the specific answer to our problem. Here is a generalized takeaway that the curvature of a circle is always going to be the reciprocal of the radius length. Okay? All right, moving on. So the unit normal vector n. This comes from t, so if we look at our drawing over here, we can see our unit tangent vector, and it shares the point here, P1, with the unit normal vector. And so we need to be able to find a vector orthogonal to t that is tangent to the curve, or it touches the curve at the same place and forms a right angle. So they call this the principal unit normal sometimes, and that's where the n comes from in its name. I'm used to calling it the unit normal vector, just like we call the other one the unit tangent vector. And here's a little fact that may not be something that you recall instantly. So since t, pardon me, that should be bolded or have this symbol over it, but it's typed. I should have bolded it. Since the unit tangent vector is a constant length of 1, the derivative dt with respect to arc length is orthogonal to, and it should have been n, I believe. Got a little bit of typos in here. Oh, no, excuse me. That the derivative dt ds is orthogonal to t. Okay, so here we have dt ds. All right, and we'll talk about the 1 over kappa in a minute. And it's drawn as orthogonal to t. And the question is, why is this true? So I'm going to refer you back to section 13.1. It was the very last idea they threw out before the homework questions, talking about the radius is always, in a circle, is always orthogonal to the tangent vector. Okay, so that's a similar thing here, because everywhere that we measure curvature, we're going to have a circle that's related to this curve that's tangent to the curve in the same place that the unit tangent vector is, and that circle is the circle of curvature, and we'll get into that in a minute. But there's always this orthogonal relationship between dt ds and t, okay? And since we want to deal with unit vectors, we're going to cut dt ds down to 1 unit long by dividing by its length. So if you remember the kappa formula, just peek back here. All right, the original kappa formula in terms of s, here we go. Kappa was the magnitude of dt ds. So multiplying dt ds by 1 over kappa is dividing it by its own length. So that makes n a 1 unit long vector. Okay, so let's go find n for a vector. Actually, right now it's in terms of dt ds, and once again we need to convert it to a formula that is in terms of, or with respect to t and not s as a parameter. This is a concept that's not going to go away, so make sure you understand the difference between operating with respect to the change in arc length and operating with respect to the change in an independent variable t. Often t represents time, especially when we're talking about particle motion. So we've got a formula here then for n with respect to t, all right? And I want you to go through this and make sure it makes sense to you. It's very similar to how we converted t from a parameter of arc length to a parameter of t. Now, n is always going to point in the concave direction. It could be orthogonal to t and go the other direction, but we're going to designate n as the unit normal vector that always goes in the direction of concavity. So the direction that the curve is concave. So concave would be inside the curve, as if this were a closed curve. N is going to go inside the curve. You see over here where the curve curves in the other direction, the unit normal vector goes toward the interior of the curve, as if the curve were closed. Okay, it's not, but as if it were. Okay, let's see, that would be interior. All right, so this is just a summary of what this page says, that we've now got our formula. We take dt dt and we divide it by its own length, and we get the unit normal vector. Okay, so this is a process. You have to get t first, and then you can get n. Okay, so we're going to find t and n for this curve, and we're going to stick with, this is obviously a circle. We're going to stick with circles and other curves that we're familiar with that spiral around the z-axis in space or that turn around the origin in the plane. So just follow along as we talk about how do we get t and n. All right. So in order to get t, recall that we need to take the velocity vector and divide it by its own length. Okay. So v of t is going to be, now we're going to need the chain rule here because we're going to have negative sine of 2t, and then the chain rule says we have to take the derivative of 2t, so we'll put a 2 here, okay? And that's in the I direction. And then in the j direction, derivative of sine is cosine of 2t, and then chain rule times the derivative of 2t, and that's in the j direction. So take a look at this. When we get the length of v, if we put this squared plus this squared, okay, we're going to get 4 sine squared of 2t plus 4 cosine squared of 2t. All right, so we're going to go ahead and start with the 4 factored out. So sine squared plus cosine squared, it's both of the same argument here. 4 was on both of these, so I'm just going to factor out. All this is just 1, so the square root of 4 is 2. So to get t is going to be the velocity vector here, and we're going to divide 2 into each component, and that's going to make our 2's cancel here. So we're going to have the unit tangent vector is negative sine of 2t in the I direction when the 2's here cancel. And then positive, these two 2's cancel, cosine of 2t in the j direction. Okay? So now we need t to get n, all right? So n is going to be our 1 over the curvature of the magnitude of dt. All right, and we could also write that as dt divided by the magnitude of dt. That's how we're going to think about it to calculate it, okay? So we need dt. All right, dt, capital T up top, lowercase on the bottom. Please be careful with accurate use of syntax. And this is a vector. All right, so the derivative of this curve, interesting, well, we get to go through very similar processes here. The derivative of negative sine of 2t is negative 2 cosine of 2t. Don't forget that chain rule. And that's our I component. And then the derivative of cosine of 2t is negative 2 sine of 2t in the j direction. And then we'll take that vector and divide it by its length. So the length is going to be, okay, we're going to square this. It's going to be on both terms. Pretty soon you get to where you don't have to see this every time. You may already be there. So all this is 1, square root of 4 is 2. And so we just have to divide 2 into each of these to get our normal vectors. So our normal vector is going to be negative cosine of 2t I plus, and over here, those 2's cancel, and we have negative sine 2t j. And you really don't have to put parentheses around these. I just do as a matter of habit. So there are our 2 vectors we're searching for, the unit tangent vector and the unit normal vector. Okay, and these are just going to go back and forth with different signs on sine 2t and cosine 2t, and these are going to switch to be cosine sine or sine cosine every time you do this. Okay, so let's do some vocabulary and relate it to this picture. So a circle of curvature is a circle that helps us understand and reproduce drawings. All right, so we have our parabola here in blue, and we picked a point P on it, and we draw a unit tangent vector. We've got that here. and a unit normal vector at that point of tangency. And then we draw a circle that is tangent to this parabola that has the exact same curvature. So this circle, this red circle, the circle of curvature, is tangent to the parabola at point P and has the same curvature at point P as the curve does. And the center of the circle lies on the concave side of the curve. Okay, so in the direction of the unit normal vector. It's going to be the same direction as that. So this length is going to end up being the radius of curvature, and the center of curvature is the center of that circle of curvature. So all this is just a bunch of vocabulary, but it's related to helping understand how curvy a curve is. And these circles I've seen used in drafting programs to make sure that when you're doing curves in various places in a design, if you use the same circle of curvature to help you draw them, then you make sure that your curvature is the same from one, open curve to another. Okay, so one more example. Oh, by the way, the other word for a circle of curvature is an osculating circle. And some textbooks use this phrase and some use this one, and ours uses both. So you'll get used to it. By the way, the radius of curvature down here has a little formula, the length of that radius. The reason why they use what looks like the letter P, it's a funny P with a different font. This is actually the Greek letter rho. It's the R sound in the Greek language. So R for radius of curvature. So they used a Greek letter for curvature, so they're using a Greek letter for radius of curvature. So rho equals 1 over kappa is how this reads. All right, so let's find the graph, and or the equation anyway, of the osculating circle, the circle of curvature for this parabola at the origin. Okay, so we need to parameterize this and do it as a vector valued function. So if I make x t, then y is going to be t squared. All right, see how I did that? If x is t, then y is going to be t squared. So that becomes r of t equals ti plus t squared j. That's a super simple thing to parameterize that curve, and you can always just substitute in t for x and then plug in t into your function formula, and that's how you can simply parameterize a curve, especially one as straightforward as the parent parabola function. All right, so we need, in order to do this, we're going to need our t vector, all right, and t requires a velocity vector and its magnitude. All right, so our velocity vector is going to be the first derivative. Derivative of t is 1. Derivative of t squared is 2t. Okay, and then the magnitude of v is going to be the square root of 1 squared plus 2t squared, which is 4t squared. All right, so to get t, we're going to do 1 over the square root of 1 plus 4t squared as our I component, and 2t over the square root of 1 plus 4t squared j. So that is our t vector. You could write it with negative exponents if you like. That's fine either way. And then we need to get dt. And this is where it gets really fun, okay? Because we're going to need the curvature, all right? And remember the formula for curvature. So we need to get dt so that we can take its magnitude. So this is fun because if you want to do this with fractional exponents, you can do the product rule as it is. You're going to do the quotient rule over here, no matter what you do. And so really quickly, I'm just going to give that to you. So we end up with negative 4t over 1 plus 4t squared to the 3/2. Alrighty, and that's I. And then when you apply the quotient rule here, you're going to get ugly stuff. All right, so we're going to have 2 times 1 plus 4t squared to the negative 1/2 minus 8t squared times 1 plus 4t squared to the negative 3/2. And that is the j component. And then we have to do the magnitude. Now, let me give you a little hint. At the origin, t is 0. So why don't we just go ahead and substitute 0 in for a bunch of stuff, okay? We could get t at 0 here, okay? We're going to have 1 over the square root of 1, so 1i. In fact, I should do this in another color so it's highly visible. Okay, so that's going to be 1i, and then t is 0. It's going to give us plus 0j. Okay, if you want to put 0j just to be a good reminder, you can. And okay, make sure I'm doing all this right. Actually, we didn't need this one, but that's what it turns out to be. So t turns out to be I. So imagine this parabola at the origin. All right, unit tangent vector at 0 is just I. Okay, that's t. And then the unit normal vector then would be this direction, right? So if I plug in 0 to this expression, so we're going to get 0 here on I. And then t is 0 is going to give us 1 to the negative 1/2 power is 1 times 2. So that's going to be plus 2. And then t squared, subbing in 0 here, this whole expression is going to be 0. So that's going to be 2 plus 0j. So here is dt dt. And then the magnitude of dt dt is just going to be the square root of 0 squared plus 2 squared, which is 2. So when we do curvature, we're going to do 1 over the velocity. All right, so the velocity at time 0, the magnitude of the velocity, excuse me, at t equals 0. So this is going to be 0. The square root of 1 is 1. So 1 over the square root of 1 times our magnitude of dt dt, which we figured out was 2. So we're going to end up with a curvature of 2. All right, now they wanted the graph. All right, so let me just do that over on the side here. We know that the center of the circle is going to be found with the radius of curvature. And remember, the radius of curvature is 1 over kappa, which is 1 over 2. So we know the radius is 1/2 unit long. It's going to be tangent to the circle at point P, which in this case is 0, 0. It's going to go in the direction of J. All right, so up 1/2. So we've got a radius of 1/2, and the center of the circle is going to be 0, 1/2. And so we need to come up with the equation for that. And that's going to be x squared plus y. I've got a cat wanting to sit on my computer now. Y minus 1/2 squared equals 1/2 squared would be 1/4. All right, so there's the equation for that circle of curvature for this parabola at the origin. All right, so let me just point out for curves in space that we just do all the same types of calculations, all the same formulas, except now we have a third component to make it three-dimensional. And these are excellent examples, but they're so similar to the ones you've already seen that I will leave you to read them. Please make sure that you do and that you don't leave out this third term when you go to do 1 in 3 space. All right, thanks for listening.